a look at our comprehensive capabilities, supercomputing scale, and AI accelerated innovation and discovery at Google Cloud. So some quick context for today's presentation. Our GCACC online presentations, the meat of them is only 30 or 40 minutes, so we have to choose to go wide or deep. Today's is wide. I'm going to give you a broad overview of our latest HPC capabilities. The deep dives into the topics I cover today will be spread out over the coming weeks and months. Every so often, we'll come back and do a broad update. So every 3 to 6 months, we'll do a broad update on quantum computing like we did last week, or AI like I did 2 weeks ago. And then we'll go into deeper dive topics over the next few weeks. We do encourage you to tune in over the next several weeks for those deep dive presentations, and also join us at ISC in Hamburg if you're going to the conference. We'll be there on June 25th for a deeper workshop on HPC, and join us in Chicago on July 15th, where we'll go way deeper. It's an entire day diving into HPC and AI. The details of both are on our website. So now jumping into this, we're going to give a little background because I know some people on today's session are HPCers, but others are from other advanced computing domains. So I just want to remind everybody how I'm going to use the terms today. HPC is high performance computing. That means it's a computing approach that delivers higher performance than mainstream. It is not a specific architecture, and it's not a specific workload. It's whatever the current method of achieving high performance computing enables you in today's time. In the past, as we'll talk about, it was Cray supercomputers. In the future, it may be quantum computers. Today, it's basically Linux cluster computers. High performance computing can be achieved with high performance processors or by aggregating mainstream processors. And we'll talk a little bit about that. So that means right now it's evolved to be clusters. In the past, it used to mean Cray or CDC supercomputers that had processors far more powerful than the mainstream processors of their eras. And they were used mainly for simulation workloads. Then we had these SMPs, or shared multiprocessors, and these MPPs, these massively parallel processing systems. Those were both dedicated kinds of supercomputers themselves that had more processors in them, not quite as powerful as the Cray parallel vector processors, but many, many more of them. But commodity tech finally won out. Collections of x86 microprocessor-based computers running Unix at first, then Linux, and working together as one cluster. So they're kind of virtual supercomputers. They're individual computers being made to work together as a virtual. I didn't say virtualized, but as a virtual supercomputer. And they started with single core CPUs, but we know all these x86 and now ARM processors have many more core processing cores than just one in each processor. So we started with single core CPUs, and now we have these many core CPUs. A major innovation was adding GPUs to these CPU-based systems and using low latency networks when you knew you were going to use the cluster just for high performance computing. But these clusters evolved to also be clouds. So cloud data centers host racks that use the same processors, memory, hard drives, and SSDs. And they've also added low latency networks. And the primary difference now between on-prem HPC clusters and cloud clusters is not technology. It's really just single purpose for on-prem HPC clusters versus multi-purpose by way of using virtual machines in clouds, although we can now do bare metal for certain things as well. Ownership versus pay-as-you-go, although we can now do committed usage discounts, which is like having your own committed cluster. Or batch jobs versus on-demand, although we can now also do different types of batch jobs in the background as well. So clouds can provide essentially all of the same technologies and capabilities now as on-prem HPC clusters, while still providing a much broader set of capabilities for enterprise and consumer applications and usage. So all data center campuses now, these AI data center campuses you hear so much about, they are basically massive HPC clusters. And that's an important thing to remember. Now, they're HPC clusters tuned for AI workloads. You can always tune your processor and GPU choices, your memory choices, your networking and storage choices to be better for certain kinds of applications and workloads. For others, these AI data center campuses, they may have multiple data centers in one campus, all networked together. Those are essentially massive HPC clusters. So the analysts have asked, what do HPC customers want from cloud HPC? And so, the customers in the past have said things like lower cost for storage or lower cost for compute, or on-premises tools to integrate with on-prem clusters and other features. And this is really important, and Google Cloud has listened to this. And Google Cloud and others are seeing market share climb for cloud HPC. Now, the overall HPC market is big. It's $70 billion. The cloud HPC market didn't exist several years ago. The clusters on-prem happened first, but these cloud service providers realized that they were providing the same technologies, and they could target that technology at HPC workloads as well. And so you can see the percentage of, in that right chart there, the percentage of all HPC that's being run in the cloud is growing faster than on-prem. And that's a really important thing, and Google's been a main driver of that, showing people that you can do HPC very effectively in the cloud. And it's growing in the cloud because of many reasons that are on this slide. And I won't read all of them, but I'll read a few. There's huge complexity in deploying and managing these large HPC systems, and it requires increasingly massive data centers and power and cooling. And it's hard to fund that and to amortize the benefits of that. So in many ways, it's better to leave it to the professionals. The people who provide very large data centers are the ones that can provide very large HPC capability. Also, individual systems are usually pretty homogeneous, but cloud service providers offer lots of different processor choices and accelerator choices and options and usage options, as we're about to see. Clouds also give better failure tolerance and continuous operations. They can seamlessly move your workloads between different cloud data centers to ensure you as the customer don't suffer as much from downtime as you would in an on-prem system. There's also a really strong AI and HPC synergy in the cloud providers, who have all invested heavily in AI, none more so than Google. And that leads to some tremendous synergies that we're going to talk about. And I'll just summarize by saying the HPC market is growing fast. The cloud HPC market is growing even faster. And let me just say, I can't share the numbers legally, but we're growing really, really fast because of the efforts we're putting in to making our cloud optimal for HPC. And we have sort of a four-pronged approach in doing that. We want to make Google Cloud fast and affordable. It has to be fast if it's HPC, but it has to be affordable. That is one of the customers' concerns when moving from on-prem to cloud, is will it be affordable? And in reality, for most, especially commercial customers, cloud providers are paying exactly the same cost as the commercial company would have to do if they did it in-house. And we can get the benefits of economies of scale. We can get the benefits you think of by just bulk buying and bulk deployment, but there are other economies that you can also get through scheduling and consumption models that we'll talk about. We have to make it easy and compatible, and we absolutely do that by using the same technologies and software that people are familiar with. We really want to be partner preferred, and I'm going to show you an example of our partner ecosystem, and that is how we can provide such great diversity of capabilities. Large companies and even small companies may run many different applications, and the same on-prem cluster isn't going to be optimal for all of them. But clouds can provide comprehensive capabilities by spanning so many data centers and so many racks in each data center. You can provide many different technologies that one customer can use the same way and use different processors, different storage options, different accelerators. And of course, we want to bring the best of Google into it. Google spends a lot on R&D, and we're driven by the desire to help people access the world's information, understand and use that information. And that has really driven our AI efforts in-house. And I'll talk a little bit about, even though this is an HPC presentation, I'll talk a little bit about how our AI technologies can help with HPC. And of course, this means we have to have diverse compute capabilities and storage capabilities. We also have to have fast network capabilities. And this is really important in cloud providers because with on-prem HPC clusters, you can choose to deploy not just a standard Ethernet network, but a very low latency Ethernet network or a special network like an InfiniBand network to help make that cluster of computers work faster and better together as a single virtual supercomputer. And that requires having great HPC software as well, because now it's that software layer that makes a whole bunch of individual computers act as one virtual supercomputer and makes it possible for you to program it. So we've made a lot of recent investments in HPC, and I don't mean for you to read this eye chart. I just want to impress you with it because I want you to see that Google Cloud has taken HPC very seriously. We are dedicated to providing great capabilities in HPC, great performance, great scaling, great diversity of technologies for different workloads. And so we've been investing in HPC for a long time, but we've really stepped it up over the last few years. So what's new with our HPC infrastructure? We've got a lot of new things. And again, this is an eye chart, and I'm going to get to some of these in the subsequent slides and many more of them in the presentations over the weeks to come. This is going to be your broad brush overview, and then we'll deep dive into many of these. But some are things like our H4D VMs, which you'll think of as AMD EPYC Turin CPUs. Arguably the most generally useful CPU technology for scientific and technical applications right now. We also have multiple GPU VMs with different NVIDIA GPUs that are optimized for things like machine learning training, 64-bit floating performance, remote visualization, and other capabilities. And we have our latest TPUs in these data centers. And this is a Google-specific technology that is excellent performance and price performance for machine learning workloads, and we're exploring its usefulness for scientific and technical computing workloads more generally. We've enabled our low latency RDMA network across many of our VM types and have tremendous networking latency and bandwidth now. And we have a number of great storage options, including our managed Lustre. Lustre is one of the most widely used parallel file systems in the world. It is a bear to manage Lustre on-prem. You need dedicated experts and support contracts. It is a powerful and wonderful capability, but it does require some expertise. And so we provide a managed Lustre capability to make it easier for you to get all of the benefits of Lustre without having to have all of the sysadmins that are normally associated with it. And we have some other great storage options too that I'll mention. So Google Cloud HPC overview. I kind of gave you this before, but it's really about flexible consumption, optimized software, and performance optimized hardware. When people think of high performance computing, they often start at the bottom of the stack. That's the foundation, the performance optimized hardware. After all, high performance computing is about high performance hardware. If you don't have high performance hardware, you're not going to achieve high performance, but you must have optimized software on top of that. And then you want to provide flexible consumption models to make sure that people can use it at the price points they want. Obviously, using a cloud on demand is going to be the highest price, but using it in a spot background mode is going to be the lowest price. And there's a range of things in between so that you can balance the priority of urgency versus the priority of cost minimization. And we think all of this together really makes us a great platform for scientific and technical computing. So HPC is a big part of this, the supercomputing class infrastructure we're talking about today. But we do layer on top of this optimized tools and libraries, high performance applications, and support and services. And we'll talk about those in future sessions. And we feed into this Google research models, Google DeepMind models, other Google services, and in the future, Google Quantum. And then, of course, we have communities for developers and users, of which this is one. Well, of course, HPC, the middle name is performance, and that usually comes from your processors and accelerators. And you can see on this chart a number of different VM options, our E series, our N series, our C series. Our H series are really optimized for high performance computing. That's in fact where the H in the VM title comes from. But our A series on the far right, bottom right, that's high performance for AI and machine learning, but those VMs can also be used for high performance acceleration in simulation applications. In addition, some of our C series VMs have Intel and our own version of ARM processors in them, and they are often very good price performance options for certain kinds of HPC applications. The real point of this slide is something about clouds and the comprehensive capabilities they can give you for running all of your workloads, your enterprise applications, your HPC applications, your machine learning applications, and more. And that's one of the things we're very proud to provide, is an environment for all workloads. One of the high-profile VM types is our AMD-based H4D VMs. These are truly optimized for HPC, and they scale seamlessly with our RDMA networking. So they have high bandwidth, 200 gigabits per second bandwidth, but they have very low latency as well. And many simulation codes, many partial differential equations solving codes over 3D domains require that very low latency to scale well. And this has been a recent addition to our infrastructure. And this enables you to build large and flexible HPC clusters that will perform and scale well using technologies like Cluster Director and Dynamic Workload Scheduler. We're going to talk about all of this coming up. But a little bit more about H4D. I just wanted you to see that as an iteration, H4D is much faster than our previous generations of AMD-based CPUs. We actually announced H4D about a year ago, but it really took much longer to bring it to full general availability. We had some limited customer access for many months. We wanted to make sure that we got it just right for you. It was performing exactly as we expected, and that it was scaling as we expected with RDMA. But now it's in full GA mode, available to customers. It's in high demand, I should say, but you can see it gives tremendous speed ups on scientific and technical applications. And a lot of that is because of the RDMA networking that enables you to not just get good performance on node from the AMD CPUs, but between nodes that are communicating with each other due to the RDMA network. And that enables your applications to scale better. Obviously, everybody would like linear scaling on everything they do on HPC clusters. It's hard to get true linear scaling, but you can get closer and closer to it as you get lower latency networks with higher bandwidth. We also have a general purpose C family of processors. The C4 series is the latest Intel Xeon processors. C4D, the D is for AMD. And so those are different SKUs of AMD processors. And C4A, our Axion processors, are our own silicon based on ARM IP that we license, and we've crafted our own very excellent price performance ARM processors based on that. And so they're optimized for performance. They have premium enterprise features, and you can run a variety of different workloads, enterprise workloads, commercial workloads, industry workloads, etc. And for different needs, you may find that C4, C4A, or C4D are the optimal price performance processors for your applications. Now, for just raw performance, H4D is probably going to be your winner, hopefully on price performance, but definitely on performance. But we're really impressed with our Google Axion performance on some subsets of HPC applications. It's a very good price performance processor. I'm not allowed to say what's coming down the line, but as you all know, all of these processor technologies advance, and we have people in-house at Google that are working on future versions of these ARM processors. That Axion family of ARM processors also includes an N4A. This community is probably going to be mostly interested in C4A for HPC applications. We also have our most powerful lineup of GPUs ever. We have been among the first clouds to deploy generations of some of these GPU technologies from NVIDIA. We have a very strong partnership with NVIDIA, and we're very proud of these A4, A4X, A4X Max, and future processors that we've said are coming based on that, as well as our G4 processors that give you very good price performance for certain kinds of applications. And so we can support a wide variety of workloads with this range of GPUs. I see some questions coming in the chat window here. Just as a reminder, submit questions using the Q&A feature, and I will come back to those in Q&A. So Google Cloud supports a wide range of diverse workloads, and this is the more AI and graphics-oriented set, but you can absolutely use these for accelerated computing and simulation applications as well. Now I'm going to jump real quickly to talk about Cluster Toolkit. We've presented this in the past in depth, and we'll present it in the future in depth again. But I have one slide on it here. It is a way that you can essentially do do-it-yourself clusters in our virtualized cloud environment. Now, several slides ago, you probably remember me saying that on-prem clusters are purpose-built bare metal for HPC applications and workloads, and clouds are generally virtualized infrastructure with a much wider range of processors and accelerators, but all of which is generally virtualized so that after each of you finishes using it, another one of you can come and get a clean image on that same infrastructure that doesn't see any of the data that you had before you released it. The new customer now sees clean VMs on that same infrastructure and may run very different applications on them. So this protects all of you from each other. It protects all of our customers' privacy, protects their data. It allows everybody to get a fresh, clean environment every time they run with no extra processes hanging around running and maybe clogging up memory and affecting performance. Cluster Toolkit makes it easy for you to either use our blueprints or create your own blueprints that are configured for the applications and workflows that you want to run. And in particular, choosing the exact VMs you want, choosing the software stacks you want to run, and more. Choosing the Linux distro you want to run on those VMs. This enables you to build a custom cluster on our infrastructure for your applications. And this is a very powerful capability, and scientists and technical application developers like this because they can have multiple blueprints that run in Google Cloud. And it's like having access to multiple on-prem clusters. Each blueprint tailors Google Cloud instances for exactly that application for its optimal performance and price performance. And then you can have different blueprints for different applications. Now, Cluster Director is a new technology, and in fact, you're going to hear about it in just a few weeks in this series. Think of this as more of the set it and let it go model, in which case you set up a cluster in Google Cloud and then it's managed for you, as opposed to you managing it, spinning it up, using it, tearing it down, virtually speaking, of course, and then spinning it up later, maybe with some different characteristics. Cluster Toolkit gives you that fine-grained control. Cluster Director gives you that wonderful manageability so that it runs just like a well-managed on-prem cluster for you. And it's got tremendous capabilities for uptime and frictionless access and control over maintenance. You get minimal downtime because, again, you're benefiting from our cloud infrastructure there as opposed to a single on-prem system. You've got fine-grained workload placement control and consistent workload performance. So Cluster Director really gives you a lot of the same feel and a lot of the same capabilities as if you had a dedicated on-prem cluster. So we've got some interesting consumption models as well. You might remember several slides ago, on-prem customers, biggest concerns about cloud HPC are often around price. And while it is true that if you just come to a cloud and want to run one job on demand right now, that'll be our most expensive usage model. But that's not the way HPC customers work on-prem. And it's not the way they should work necessarily in the cloud either. We do have an on-demand model, and that is really powerful when you need a lot of processors now to run something urgent. In fact, that can be challenging to do in an on-prem cluster because chances are the on-prem cluster is running something like Slurm and has lots of jobs already submitted and waiting, and you can't get an on-demand application to run. Our vast scale makes it possible in many cases for you to get even very large numbers of resources all at once, but that of course is the premium model. Now, you can also use things like CUDs, or committed use discounts, or flex CUDs. And these are when you buy a certain amount of guaranteed usage of Google Cloud. We then guarantee you that usage, much like an on-prem cluster, and we give you a substantial discount for using it for HPC. And you can see the numbers on the slide, up to roughly half. That can be tremendous. It's cutting your cost of computing in half in return for just using it in a very similar way that you'd likely be using an on-prem cluster. So factors of 2 are huge in cost, right? And so that is a tremendous advantage. Spot VMs can be discounts, and this says up to 60%, but they can actually be even greater than that in some cases. This is if you're willing to wait, if urgency is not the important thing, but cost and completion are. Spot VMs can be tremendously useful in getting you very, very large discounts as long as you're willing to wait a little bit. And we've recently introduced something called Dynamic Workload Scheduler, and that has 2 modes. It has a flex start mode and a calendar mode. The calendar mode works a lot like Airbnb. You say what you need, and it tells you and when you'd like it to be, and it helps you set a time-based reservation for when it can guarantee access to that number of resources at once for your application. Obviously in the same data center, because it's an HPC application, you want co-location of your VMs. These modes on DWS can also give you roughly half level discounts on running HPC jobs. So really you can see there's 4 or 5 ways on this slide alone of making sure that you're not ever paying the on-demand price, which is very important to certain commercial customers that are doing real-time simulations, real-time analytics of incoming data, et cetera. When you need it, we can facilitate that scale. But if you're running jobs that you would normally run in the background, which is common in HPC research and pretty common in HPC engineering as well, engineering simulations of new car model, structural models, take out weather forecast, structuring, any kind of structure or fluid models. Generally, you can afford to run those in batch in the background and take advantage of that on-prem. We have models for you doing that here as well. So Dynamic Workload Scheduler is a really powerful capability. It doesn't work with all of our VMs yet, but it does work with H4D, GPUs, and TPUs. And again, it has these flex start and calendar mode options for in return for you giving us some flexibility in when it runs. We give you the discount based on our vast scale, and this economy of scale and being able to schedule things in there enables us to pass that savings back on to you. So flex start is just-in-time capacity for defined duration jobs, and calendar mode is reserve capacity for, say, longer ML or HPC jobs. I do want to give a shout out to our great partners, by the way. I've mentioned some technologies along the way, and I'm going to mention a few more. Mention some CPUs and GPUs, and I'm going to mention some storage coming up. We have a wonderful partner ecosystem. This slide is not up to date because it's never up to date, because we're always welcoming and embracing new partners that expand our capabilities. I said at the beginning, clouds are very good at providing comprehensive capabilities as opposed to homogeneous, single purpose on-prem systems, and yet can still give you the capabilities at scale of those on-prem systems. But in giving you those different capabilities, you have to work with a lot of partners in an ecosystem, and probably many are on this call right now. If any partners are on this call, I hope some of them will give a thumbs up or something here. Some of our partners are also customers as well. They both partner with Google, and they use Google for their simulations as well. So great partner ecosystem, and that is a great big part of why we can provide such comprehensive capabilities. HPC storage on Google Cloud. We have an upcoming session on this, and again, today's is the broad brush overview, but we have a lot of great capabilities. Some are Google's native, some like Managed Lustre are provided with partners like DDN. We also have great partners like SciComp and Vast and Weka in our storage portfolio space. So we have tremendous high-performance storage solutions and AI and data platform solutions for you to use as appropriate, as best fit the needs for your HPC applications. Again, this is a capability that is much easier for very large cloud providers to provide, because generally in an on-prem system, you want to limit the range of features you're integrating together to make it more manageable. But we can implement different features and different capabilities in different parts of data centers and in different data centers to provide a global network of cloud data center capabilities that have a tremendous range of options for you to use. And your applications and workloads are going to be varied, and sometimes different storage solutions are just as important as different CPU, GPU, and accelerator technologies. Now, we're already getting close to the end of our time, and there is far more to talk about with HPC at Google. More details on CPUs and GPUs.
Oi, gente, Yara aqui. Em que posso te ajudar hoje?
Not quite sure how someone's AI note taker is able to speak here, but let's just remove that from the call. More details on CPUs and GPUs and our TPUs coming soon. Our TPUs you've probably heard of. Their public usage has been limited to a subset of HPC workloads, specifically AI model training and inferencing. And we'll talk about that, but also at how they may be useful in more broader scientific and technical computing applications. And that's coming up in about 6 weeks. We're going to talk about more storage options. We have more storage options now and more coming soon, and we'll talk more about that over the coming weeks. We're definitely going to provide more details on Cluster Director and Cluster Toolkit in the upcoming weeks. We'll talk more about how to deploy and manage clusters and develop and optimize applications and workflows and optimize your own costs using these consumption models. I did it very lightly today. We'll have dedicated sessions in the coming weeks and months on this. So these are topics for these dedicated sessions, but you can also join us for workshops at ISC 2026 on June 25th and in Chicago on July 15th to really dig in. AI can help accelerate human efforts, code, and systems as well. So while this presentation has been an overview of HPC, I want to remind you that Google is a world leader thanks to our folks in Google DeepMind and Google Research and the tremendous work that they're doing in AI technologies. And Google DeepMind is really driven by the desire to solve important scientific problems. So they provide models and tools built on those models that are very useful for scientists. Co-scientists and hypothesis generation, which was just announced, helps explore new ideas. Anti-gravity 2.0 can help develop even HPC codes faster. So if you were wondering if anti-gravity 2.0 was just for developers of web applications and enterprise applications, the answer is no. It can help you develop HPC codes faster. Alpha Evolve can also be used to optimize HPC applications and many more kinds of applications as well. Gemini Enterprise Agent Platform provides a comprehensive set of agentic capabilities for creating agents that can be used to create smart workflows for your HPC applications. And AI can even power its own discovery apps and surrogates for simulation apps like AlphaFold 3 and WeatherNext, which we've talked about in the Google Cloud Advanced Computing community in the past. And we'll talk about more applications of that type in the future, as well as explain how to build your own AI surrogate applications. Now, a really important thing about these surrogates that I'll say before we move on is HPC simulation applications are based on physics and have been sort of the ground truth of what we trust in computational science and engineering. These AI surrogate applications can be trained on observational data or the output of trusted simulation applications, and then once trained, can be much faster than rerunning simulation applications. So there's a wonderful synergy between physics-based simulation applications run on HPC clusters and these physics-informed AI surrogate models run sometimes on single node, because running AI models, not training them, but running them, can be very efficient and quick. So we're going to talk more about that in, I believe, the end of August. So these are also topics for dedicated sessions coming up and also covered in our upcoming workshops. So with that, I'm running out of time, and I'm going to summarize this broad brushstroke conversation of HPC at Google by saying that we can deliver supercomputing capabilities now by using the latest processors and the latest GPUs, and soon maybe the latest TPUs, stay tuned, to really make your applications hum. And by using RDMA and NVIDIA's own InfiniBand technology between some of our GPU instances and our own optical networking technology between our TPU pods, we can really make these things scale as well as perform. And then we have storage options to keep up with these performance applications. So Google Cloud is more powerful with the latest AMD and NVIDIA and also custom ARM, and I left Intel out here, but Intel processors and our own TPUs, and scalable now than all but a handful of dedicated on-prem HPC systems in the world. There are absolutely a few 9-figure dedicated on-prem deployed HPC systems, often at national labs in the US and beyond, that were built specifically for doing HPC and can perhaps slightly outperform and outscale even clouds for single jobs. They certainly can't outscale clouds for many, many jobs because global cloud data centers are massive. But they can run dedicated applications at slightly greater scales and performance. But that gap has really been closing as Google, and not just Google, but all of the major cloud providers are really embracing HPC workloads and tuning their software and their networking, as well as using the same processors and accelerators and storage systems to provide that HPC performance at scale. I will say that while Google Cloud HPC is straightforward to use, it requires expertise. All HPC requires expertise, but using a cloud environment that is a environment that supports a wide range of applications and usage models, as opposed to being a dedicated HPC system all the time, that requires a little bit of additional expertise. And that's okay, because that additional expertise can also help you in non-HPC applications and large-scale data analytics applications and enterprise applications. So we encourage you to master Google Cloud overall, and that will really help you optimize your efforts when using it for HPC. And again, we're happy to share expertise in that in the weeks and months ahead. And a final reminder, we are a leader in AI as well. And our HPC team at Google is really serious about teaching that AI to HPCers, how to develop research plans in which you're going to use HPC, how to develop HPC codes, how to optimize those HPC codes so that you get the maximum performance and also the best cost in running those jobs. So we hope you'll come to ISC and or the Chicago workshop for more details and hands-on labs, in particular in Chicago. And then instead of 30 or 40 minutes, we can spend an entire day with you. We can have you run through some things. You can try out some applications and some simulation codes. You can use our AI tools as well. And we think we can really help you become much more effective in your day jobs of scientific and technical computing. And with that, Mary, I think we're back to the main presentation and the Q&A. So I'll stop presenting so Mary can bring up the previous deck. There we go. So I will take Q&A before we talk about our next things here. Oh, wow, 9 new questions. This might be a record for us. So let's see what we've got here that I can answer relatively quickly in this session. Uttara Sawant says, do you collaborate with UT Austin HPC Lab for architecture and infrastructure requirements? Thanks. Uttara, we do not collaborate with UT Austin and other centers in terms of our own infrastructure requirements directly, but we go to the same meetings. I just talked to Dan Stanzione, the director of the center there, at a previous conference. So we share information globally about performance of these technologies, and then every center and every cloud makes its own decisions based on performance, expertise, projected future workloads, et cetera, on the exact infrastructure they're going to provide. Dan and TACC at UT provide the best on-prem HPC systems of any academic supercomputing center in the world, and they've got a new big one coming. So huge kudos to them. And they go to these conferences and share the information that they present. We do the exact same thing. We build powerful clouds and we go to conferences and share that information. And of course, lots of the leaders from these things talk with each other. I just saw Dan at the Trillion Parameter Conference, I think about 2 weeks ago, and I'm sure I'll see him next week at ISC, along with the leaders of many other academic centers, labs, and many other vendors. The vendors don't share the same kind of information that the academics and lab folks do. They're very open about publishing. The vendors keep some things a little bit close to the chest on when it's a competitive advantage. Let's see. Let's see what else I'm going to answer here. Kai Park says, the dynamic workload schedule looks really impressive. It is. Thanks for the explanation. The dynamic workloads, then just repeated that. I'm wondering if the platform already supports combining the dynamic workload scheduler with the CUD resources feature for atomic provisioning. I'm not sure the answer to that, Kai, but if you send an email in to gcacc@google.com, I will find the answer for that and reply to you. Kamiswar Akela says, please share the ISC 2026 on June 25th registration URL. Mary, I'm sure you've probably seen that and shared that in the chat, but if you haven't, would you please share that in the chat so Kamiswar and others can sign up for that? And Mary gives a thumbs up. Also, I think I might have got the date wrong on the Chicago workshop. I think the workshop is on July 14th. And then there's customer NDA meeting opportunities if you want to go deeper on July 15th, if you stay overnight. And there's a reception that night, so you should. So I believe, I hope I see a lot of you on July 14th in Chicago and the morning of the 15th. Mary, did I get that right this time? Give me a thumbs up if I did. Oh, it's the 15th and 16th. So sorry, I had it right in my slides. So come on the 15th, come to the reception on the 15th and stay on the 16th. Thanks, Mary. I got a question here. Mukesh Sharan asks, 1, what do you think about the HPC market in Southeast Asia? And 2, do you have any footprints / offerings in HPC in Southeast Asia apart from Singapore? That is a great question, Mukesh, and I'm not as familiar with Southeast Asia as I am with Japan and Korea, having been to both of those two recently. We do have Google folks in the region, and we are absolutely happy to set up customer briefings in that region. And the Asia community overall is about roughly between 1/4 and 1/3 of the overall HPC market. Google, of course, is a global company, so we certainly care about that market. I don't think we have a lot of customers in that market for HPC right now, but if there's something in particular that you want, an introduction you want to make or a meeting you want to schedule, please email us at gcacc@google.com, and we would be happy to set that up. I'll also point out that the SC Asia meeting, an annual meeting in the Asia region of the world for supercomputing and HPC, is next March in Singapore. So Google will absolutely have a presence at that. There are really 3 major meetings for HPC, AI, quantum, sort of large-scale computational science in the world. There's the Supercomputing Conference every November in the US, the ISC Conference every summer in Germany, and then the SC Asia meeting every sort of January, February, or March. It was in Japan last year. It's going to be in Singapore again next year. Let's see what else. Timur Bazarov says, Jay, regarding GCP Cloud HPC's current rapid growth, does it include AI and LLM vendors like Anthropic or only traditional HPC, scientific and technical computing? Anything you can share regarding educational and government public sector HPC engagement with agencies like DOE, NSF, etc.? Okay, it's a long answer, but I'm going to try to give a concise one. And then Tim, I know you have my email, so you can reach out to me. Our HPC numbers only include, and they're very good numbers, and yet only include scientific and technical domain applications from domains such as engineering, manufacturing, energy, healthcare and life sciences, financial services, weather prediction, etc. We do not count the revenue from model training customers like Anthropic in our HPC revenue. Now, you might say, well, Jay, why not? You said that HPC is an approach to computing, and simulation, data analytics, and AI are workloads that run on HPC systems. I maintain that is absolutely true, but how a company organizes internal org charts and budgets and reporting and things like that, that is going to be more influenced by customer verticals and things like that. So in that way, Google delineates AI specific customer spends and tracks that. And of course, if you read our quarterly reports, you know that was growing very well too. Tracks that separately. So Anthropic revenue to Google Cloud is in a different bucket. In terms of sharing regarding our educational and government and public sector, I would say our HPC team is grown a lot in the last year and a half, and we are ramping up our participation in public sector conferences. In fact, Megan Golick, who's on this call, makes sure that we're attending now and participating actively in and sponsoring all of the major conferences that draw from those public sector groups, that we're presenting our best capabilities at those, that we're presenting tutorials and keynotes and panels and so on at those. And we're increasing our partnership level of engagement slowly but surely with individual agencies and labs next. I can't say too much about that on this session, but I would say the gradient is a steep positive gradient on everything in the second part of your question, Kimmer. Got a question from Mukesh Sharon, who asks, is cluster director like BCM from NVIDIA or HPCM from HPE? Mukesh, I can't answer that question knowledgeably because I stopped following Bright Cluster Manager when I left Dell Technologies a few years ago. Great respect for Bright Cluster Manager. I always personally thought that Dell should have bought Bright Computing, but NVIDIA bought Bright Computing and it's done a great job with it. But I don't know that Bright Cluster Manager has the flex start and calendaring scheduling capabilities that DWS has. I'm not sure that that was a priority set of features for BCM, which is primarily for on-prem scheduling, as opposed to what we wanted in Dynamic Workload Scheduler, something that really leverages our vast scale to enable different ways of giving discounts, as long as you can give us some clues on what you need and how urgent it is. It's possible BCM and HPCM have some of those capabilities now, but BCM did not, and neither did HPCM when I last looked at them 2 or 3 years ago. Mukesh also asked, C4 is a new class of compute after C2s. Yes, in general, the number increases by 1 as we deploy new generations. The first letter gives you a hint as to it's kind of just a hint, it's not a rule, but more of a hint as to the kinds of workloads, like general compute, or G for graphics, or A for accelerated computing, which also uses GPUs, but not for graphics. H for high performance computing. So the first letter gives you sort of a hint as to the kind of workloads. The digit gives you a generation, and you can see by these low numbers that, again, Google Cloud is recently investing in, it's done several generations of all of these, but it's recently used this nomenclature scheme. So we're up to sort of 4 for several of these, or A5 Max was announced as well. So we're up to sort of 4 and 5 generations of some of these. Then the final letter, if it's not there, it's Intel. If it's a D, it's AMD, and if it's an A, it's ARM. By the way, I always forget that, so I'm glad I remembered it today. I sometimes have to sit and think, which CPU or GPU is this? Let's see. I think I have time maybe for one quick one. Yes, DRMA, I'll answer that. Is the RDMA typically RDMA over Ethernet? Yes, that is true. Of course, we are tracking the Ultra Ethernet Consortium efforts and various other fast Ethernet efforts as well. This is our own Falcon technology is what it's called. It's our own version of RDMA over Ethernet.